Today I'm going to talk about a learning-enhanced particle method for Landau equation, and this is based on joint works with my student Wang. So we are in the area of big data. So everything is data-driven. Even the title of this workshop is data-driven. So actually, I feel that this generation of students is different from my generation. So students care less about equations. They don't want to learn equations. They don't want to learn numerical analysis. They only want to learn data. But as Professor Osher said yesterday, that PDEs and numerical analysis are very important. So I would like to say that PDE is still the universal law for scientific modeling. But actually, based on these talks until today, you see that the paradigm does shift a little bit. So with the increasing power of computers, current paradigm is we want to deal with high-dimensional problems. So, and also we want our solver to actually integrate data into the solver. So with that being said, this neural network does serve as a promising tool. So I don't think I need to go through this. Professor Haoming Zhou has already given a very nice introduction on that. So basically, what you have seen here is this deep learning has been very successful in this scientific machine learning, either through learning the solution or through learning the solution operator. Actually, you also see in this morning's talk that there is a foundation model. So that's probably the next step. But what I'm going to talk about today is actually falls into the first category. So I'm just learning the solution. So given the setup of the equation, so the method I'm going to introduce, we want to mitigate the curse of dimensionality. So I'm not claiming that we solve this curse of dimensionality. But at the same time, we want to preserve the physical fidelity. So basically, what you can expect is this method is a combination of deep learning with the structure preserving method. And also importantly is that we want to use this neural network in a minimum way, because we don't want to throw every difficulty into learning a neural network. Because if you have experience of training neural network, it's not an easy task. And also, as Rongjie mentioned this morning, is that if you want to prepare data and to train a neural network, this data is also very expensive to get. So the method I want to introduce is that we don't need to prepare any data. So this is the outline. First, I will introduce the equation I'm solving here. So it's the Landau equation, which may not be familiar to most of the audience, but hopefully I will explain you through it. And then I will introduce these two approaches. One is a score-based approach, and the second is the JKO-based approach, and then some conclusions. Landau equation is actually one of the most important equations in kinetic theory. If you're not familiar with kinetic theory, basically this is the general form of the kinetic equation. So this F is the quantity of interest. And this F actually lives in the phase space, so it depends on T, X, and V. So this is in contrast to, for example, Hamilton-Jacobi equation, which only lives in physical space that consists of T and X. So we have this additional variable, V. And, but nevertheless, today I'm only going to focus on the spatially homogeneous version, which means that I'm going to assume F is homogeneous in X. So I'm only focused on this red part of the equation. And what is Q? Q is of this form, which looks a little complicated. But you can see that it's an integral form, and it's a nonlinear operator on F. But it's a quadratic nonlinearity because it models the interaction of particles, and it models the binary interaction of particles. So that's why it's quadratic nonlinearity. And actually, if I hide this integral operator and hide all the rest of the thing, you will see that it's the divergence of something times gradient of f. So this is like a Fokker-Planck equation. So you can just view this Landau equation as a non-local version of Fokker-Planck equation. And this A is the collision cross-section, and it takes this form. Basically, you can forget about the detailed form. And here I'm listing some physical parameters. There are some important properties of this operator Q. First, let me rewrite it a little bit. So I'm rewrite it into a more symmetric form. So this gradient f, I'm write it as f times gradient of log f. So now it's more symmetric in v and v star. And then I can write down the weak form. Basically, I'm multiplying this one by phi of v, and I'm integrate against v. And because this now is symmetric in v and v star, so I can do integration by parts and move this divergence to the test function, and using the anti-symmetry between v and v star. So I can rewrite the collision operator into this more symmetric form. And the good thing about this weak form is that if I plug in phi equals 1v and v squared, I immediately get the right-hand side equals 0, because when phi is 1v, this term is automatically 0. And when phi is v squared, this is v minus v star, which is in the null space of this matrix A. And also, if I'm plugging in phi equals log f, then this term becomes gradient of log f minus gradient of log f star, which is the same as this one. And because this A is a non-negative matrix, so I get the right-hand side is less than or equal to 0. So that is where I get entropy dissipation. So in fact, this conservation and entropy dissipation will lead to this, non-trivially leads to the following fact, that this Landau equation actually has an equilibrium, which is of this Maxwellian form. So it's a Gaussian distribution in V, where this mean and the covariance depends on the macroscopic quantity of your F. Okay, so those are the important properties of this Q. So we want our solver to preserve all these properties. At the same time, it has this scalability. And in fact, so there are many works already existent for computing this Q. So here I've listed a few popular approaches. One is this discrete velocity method. Basically, you can just consider you lay out the grid and approximate the integral using quadrature rule and a derivative using finite difference. And also a spectral method, which introduced shortly after the spectral method was introduced for Boltzmann equation. And the original version does not conserve momentum and energy. So later, 17 years later, people come up with the idea of exactly preserve this momentum and energy by writing it as a constraint. And another one is to view this Landau equation actually as a reaction diffusion. So, so this is more like a Fokker Planck. The thing is that this A and this capital A and little a depends on F non-linearly through an integral operator. And also there is Monte Carlo method either through DSMC, so direct simulation Monte Carlo, or using the SDE formulation. So all this method, of course, has some merits, but also has some issues. Like the first one, no scalability because you lay out the grid. And the spectral method, you immediately lose positivity. And also there's no entropy decay for this one. And this one is also on the grid, so it doesn't have scalability. And for Monte Carlo method, you always have the statistical error and also no entropy decay. So the method I'm going to introduce today will have all the properties, desirable properties. Okay, so first is the score-based approach. Actually, the idea is very simple. So it's based on this reformulation of the Landau equation. So it's based on, so remember I have this log form. So it's F times F star. So I just move, because this F does not depend on V star, so I just move it out. And then the whole thing is just a velocity field. So basically, you can just consider this is a continuity equation with just a very ugly looking velocity field. But as long as it's a continuity equation, conceptually, you can use the particle method. So here, because this operator is acting on V, so let's say for each particle, I'm assigning a velocity, but you can just view it as a location. And the time derivative of this Vt equals the velocity field evaluated at the current location of the particles. And so you can update. So you can update the particle location of velocity. And then every time, if you want your density, you can just reconstruct density using the sum of Diracs. So that's just the basic concept of particle method. But you may already see that there is an issue with it. is that this E, so originally this is just log F, but I'm just writing it as an entropy term. But the issue actually comes from this term, is that, so this term depends on log of F. And if your F is the sum of Dirac's, then you cannot make sense of a log of a Dirac's. So, so a simple cure is that you regularize this F. So you convolve F with a modifier. And that's actually the approach taken by Degon and Museles in the 90s. So they directly regularize this F, and then everything, you can just propagate everything over time. In 2020, we actually do a slightly different thing. Is that instead of just regularize this log F term, we go back to this entropy term, and we regularize the entropy. And the purpose of doing that is that then we can show that with this regularized version, we also have the entropy decay. So you see that the only difference between these two is that with this regularized version entropy, you actually have the entropy decay of the particle method, whereas this one, the entropy decay is lost. Okay, so in terms of structure preserving, this is all good. But in terms of efficiency, this is not good, because the regularization, so this, at that time we call it regularization, but now it's actually a popular name, it's the density estimation. So, so in order to compute this F epsilon n, you need to compute this guy, which is very expensive if n is large. So actually, that's actually the bottleneck of this approach. So is there a way to reduce the computational cost? Actually, if you look at what is the troublemaker of this approach, it's this guy. And from Sitin's talk, you already see that this is the school function. So basically, is that why do we need to go from particles to do the density estimation and then take the log and then take the derivative? We can just directly estimate this guy. So the idea is as simple as we just do the score matching. And there is a very simple trick for the score matching, very effective, that say you approximate this score function using this S theta. So we are using neural network, but it doesn't have to be neural network. It can be any other approximation you like. But then you just you just expand this square, and this is what at the end you have. So everything is integrated against F, so you can represent everything in terms of particles. And this idea has actually been taken for, to solve the Fokker-Planck equation. So here I'm listing the simplest one, the heat equation, and where the velocity field is just the score, negative of the score function. So people have taken it differently. So there are two different ways of doing it. So one is do it sequentially, so that to say at every time step, from the current set of particles, you learn a score function from here, and then you propagate your particles. And then with the new set of particles, you learn a new score function. Or you can learn a time-dependent score all at once. So this is the approach we will take for Landau. So you can see that our method is as simple as this is the original equation. Every time step, we learn a score function, and then use the score function to update the velocity. And that's it. And then the question we ask is that, say, if you want to have a little control of the error we make using this score matching, so this is the error estimate we have. So under some assumptions on this collision cross-section, this is the estimate we have. In fact, this estimate is not hard. So it's actually following this work by Bonfi and Van den Eyden for the Fokker-Planck equation. So what this error is telling you is that, so this F tilde, you can consider that's the solution to the exact Fokker-Planck Landau equation. And this F is the solution to the Landau equation with a learned score function. And you can see that this is the error you make at F, so at the density, and is controlled by this error. So what is this error? So this delta is actually the true score minus the score you learned. So actually, this one is nothing but the score matching error. So basically, this error estimate is telling you that this score matching error solely controls the error you make in the density. And let me show you one result. on the efficiency and accuracy. So, so on the left, this is the efficiency. So what we are comparing is just compute the score, because that's the most expensive part in the computation. So what we are comparing to is we call it the blob method. Basically, it's the regularized method that I mentioned. So it's not surprising that that method is the order n squared computation, whereas if we do score matching, it's just the order n computation. And this one is to show the accuracy of the method. So we are considering one specific solution where we have exact formula. So here is the accuracy in time. So here, because we are using simple forward Euler in time, of course we can extend it to high order in time. But we are using forward Euler, so we see a first order in time accuracy. And here, this one, so one thing I didn't mention is that there is a byproduct in this approach, is that you can get a density update formula. So you don't need to do density estimation at all, but you can still get the density. So, so I didn't put the formula there. I will show that in the next part. But if you're using this density updating formula, you can get the density and you compare to the exact formula. And this is the, and we run it 20 times and average over this 20 times. And this is the statistical error we get, which is order 1 over square root of n. Okay, so that's for the score-based. So you can see that this approach is very simple, but it's a forward in time method. So we know that for time-dependent problem, if we do forward in time, you will suffer from this stability constraint. And also, there's one thing I actually hide under the rug is that, so I say that in the 2020, when we do this particle-based method for Landau, we actually regularize the entropy so that we will have entropy decay at the particle level. But when we do this score-based, actually those properties not preserved exactly. So here, the second approach I'm going to introduce will have these two additional properties retained. So it will have unconditionally stability and unconditionally entropy decay. So, so for that, I probably need to explain a little bit. Rongjie has already mentioned, but bear with me that I still need to explain a little bit on this gradient flow and the JKO scheme, because the method is based on this framework. So most of you are already familiar with this gradient flow. So you have a time-dependent curve that evolves in the steepest descent direction of some energy functional. And this gradient is taken with respect to the metric you impose in the space. And so this JKO scheme is a very nice formulation to solve a time discretization to solve this gradient flow. Basically reformulate into an optimization problem. So, so you are given the density at time n, and you want to get the density at the next time step. You write it as the minimization of this summation of two terms. One is the distance to the previous density, and this distance is measured on the metric you impose on this space. And then there is additional energy term, which is the energy that the gradient flow is defined upon. And if you are not familiar, if this one is you are not familiar with this formulation, you can just always go back to the simplest version where, say, you consider the L2 metric and then consider this Dirichlet energy. Then you write down the Euler-Lagrange equation, you get this backward Euler scheme. So basically, you can, in your mind, you can just think that this JKO scheme is just a variational formulation for this backward Euler scheme. And because of that, you can see that because it's the implicit Euler scheme, so you get this unconditional stability, and also it's just one line of proof to show that this energy will decay along the dynamics. Okay, so to describe the scheme for the Landau equation, I need to consider the Wasserstein gradient flow first, because I need to explain the components in the Wasserstein gradient flow and then parallel it with the Landau equation. So let me start with the simplest equation, the heat equation. And most of you probably already know that this heat equation can be written as this form, which is a Wasserstein gradient flow of this entropy term. And And also, Siting has already mentioned the Wasserstein metric. And here I'm listing two of them, which will be relevant to the Landau metric I'm going to introduce. So one is the original one, is the Monge's definition. Basically, is that if you are given two densities, then you want to find the transport map that moves your rho 0 to rho 1. And out of all those maps, so all those maps that is the push-forward maps, we just want to find the one that has the minimum kinetic energy. And another one is the dynamic formulation. So because you can see that original Monge equation is that, Monge formulation is that you have this constraint, this push-forward constraint, which is not easy to compute numerically, because this constraint is highly degenerate. But this dynamic formulation is nice, is that it actually lifts the dimension by 1. So it introduced this additional inner time. So for these two densities, you actually consider a path that connecting these two densities. Okay, so and also another thing that related to this Wasserstein gradient flow is this entropy dissipation. Because it's a gradient flow, then this energy will decay over time, and this is just a simple calculation to show this. Okay, so these are all familiar stuff. And now we want to extend it to the Landau equation. So for Landau equation, now it looks a little bit complicated, but you don't need to read these details. Basically, I just want to introduce these two notations. What you need to understand is that for this delta tilde, it takes in a function, a scalar function, and output a vector function, depends on v and v star. And this delta tilde, so this divergence tilde is the adjoint of this operator, and it takes in a vector function. It takes in a vector function and output a scalar function. Okay, so you can forget about all this and just directly jump to the clean form of Landau equation. So basically, after introducing this tedious notation, then we can rewrite the Landau equation in this more clean form. And you can see that this one looks more friendly, because if you just replace this one by divergence, and this is gradient, and forget about this f star, that's just a Wasserstein gradient flow. Okay, so now the thing is that how do we view this Landau equation as a gradient flow if we were to use JKO scheme, right? We know that for a gradient flow, for the definition, you actually need two components. One is the energy, and the other is the metric. So for the Landau equation, we already know what's the energy, because it's the entropy, because the physics tells us that the entropy needs to decay. So there's no choice for the energy. So here is the entropy. So then the question is, what is the metric? So let's parallel it with the Wasserstein gradient flow. So these are the components of the Wasserstein gradient flow. This is the original equation. And this is the energy dissipation formula. And so these are the two components directly akin to the original equation. But if you recall the dynamic formulation of the Wasserstein 2 metric, it's minimizing this guy. And if you compare these two guys, it's just minimizing the entropy production rate. And subject to a continuity equation, and this continuity equation is the original heat equation. So basically, the thing is that I'm replacing this velocity field here and here by some unknowns v, which you need to learn. So in other words, is that if you just look at the Wasserstein metric, you can learn that how do we define the Wasserstein metric? Formally, is that you are minimizing the entropy production rate subject to the original equation. And now if you look at the Landau equation, is that this is my original Landau equation in this clean form. And I can also write down the entropy dissipation rate, okay? And then I can define, okay, actually it's not I define, so I should cite the paper. So define the Landau metric is that I'm minimizing this entropy production rate, but also replacing this guy as V, and subject to the original Landau equation, which is this form. So actually you can see that every component is the same. It's just a little more complicated. Okay, so, so this is very clean, but not friendly for computation. So let's expand everything, because we know that what those two things are. So let's expand it using just more friendly notation. So again, this is the entropy production rate, and this is the original Landau equation. So this is the Landau metric. So I really should cite the paper. So this metric actually, so I know this formulation like 5 years ago. And when I look at this formulation at that time, so at that time I think everything on the grid. And then you will see that if you look at everything in the Eulerian viewpoint, that this form looks horrible. Because you have this integral, double integral, triple integral. So if you have a grid and you have to write every integral into quadrature, so that's too complicated. And how do you do the optimization over those complicated equations? However, if you look at it from particle viewpoint, so everything is clean. Because every integral you see is against some f, which integral actually helps you in the particle formulation. Because if you have this integral against f, it's just expectation. So now you can see that you can represent everything using particles. And yes, so now, okay, so now this is, I plug in this Landau metric in the JKO formulation, and just as a sanity check of what we are, because here we are optimizing over U, and you can do a sanity check to see what exactly you are looking for, and not too surprised that this U should be a score function. And then now in practice is that these two things you can just use particle representation. So this term and this term can be easily represented by particles, because this one is again a continuity equation with this velocity, but this velocity is integrated against f. The only caveat is this f. So because you have the entropy term, so you see that, okay, we still need the f. But the good thing is that, okay, so let me just quickly go through this, is that, okay, now if I want to represent everything using particles, I'm introducing this flow map. So, so flow map, just what does this flow map do is that you input maybe to input the previous location of particles, and you output the location of particles at any later time tau. And the time derivative of the location will be your velocity field. And this flow map also push forward your density. And so this is the continuity equation that you see previously, so it's not surprising that. So what I want to emphasize here is that for the entropy term, because the entropy term is also something a little complicated, that if you only have particles and you want to compute entropy, it's not so straightforward. But the good thing here is that we are borrowing ideas from this neural ODE, is that you can, okay, so this is entropy. So we use this instantaneous change of variable formula. So for the simple focal plot, or for the Wasserstein gradient flow, this one is just the divergence of the velocity field. But for the Landau equation, it's just more complicated. But even though it looks complicated, but again, everything can be represented by particles. So that to say, you don't need to do density estimation at all. What you need to do is that, again, you compute this log determinant, the determinant of the gradient of the map, and then plug into this formula to get the entropy term. Okay, so that's it about the algorithm. So what I want to show you here is two results to show the effectiveness of this method. So first is the stability, because this is the implicit version. So stability is one big advantage of this method. So what I'm showing you here is that so I have a coefficient here, which is relatively large. And I'm contrasting with the score-based approach that I introduced previously. And you can see that for the score-based, if I'm using, even with a very small time step, the solution actually doesn't give me the correct solution. But for the JKO-based, with this tau equals 0.1, so it's actually 10 times larger than the time step I'm using for the score, you give me the correct solution. And also to show the efficiency, so here it's again to obtain the score function. So I'm contrasting with blob, which is again order n squared. But for the JKO base and score base is order n. So the JKO base is slightly more expensive than the score base, which is not surprising because our objective function is much more complicated here. But the scaling is order n. And OK, so this one I didn't say too much. So once you get the score function, or once you do the JKO step that you learn this U, you still need to propagate your particles. And those is still an order n squared computation. But there is a very easy way to reduce the computational cost using this random batch method. So that's where we are using the random batch so that it reduces to order n computation. So in total, this algorithm is order n complexity. And so here is to show the accuracy of the, I believe, OK, this is a 10-dimensional case. So this is an artificial case. It's not a physical one. So for 10-dimensional case, we also do this problem and show that for the accuracy is like 1 over square root of n. OK, so to conclude is that I've introduced this learning enhanced particle method. Hopefully, I've convinced you that it has this structure preserving property as well as the scalability. And for the scalability, it's making it possible because we are using this sampling-based particle method and also using neural network approximation. But as you can see, the neural network is just approximating the score in either approaches. So we are using a very tiny size of neural network. And also, there is no density estimation needed because we have this exact computation of density. And the stochasticity, I'm referring to the random batch. And also, there is minimum training. So currently, we are extending it to the non-gradient flow system. So like adding the spatial spatial dependence. And of course, the next step would be to do the solution operator. So you can check out Xue's poster, or Xue actually will give a talk tomorrow. It's not on Landau equation, but on the Wasserstein gradient flow. So you can consider Landau is just the next step. But the idea can be easily adapted to here. So these are the two references if you are interested. And I think that's all for my talk.